of the engine management system. Or should I say, engine management is now a part of the emission control system. The drive for cleaner and more efficient vehicles on our roads has contributed to significant increases in drivability, power and reliability. Automotive emissions that are of great concern to technicians are hydrocarbons, oxides of nitrogen, carbon monoxide, carbon dioxide and oxygen. These emissions not only contribute to air and water pollution, but can be used to determine the operational efficiency of the vehicle's engine and associated systems. Not all exhaust emissions are monitored or controlled by the management system. One such is sulphur dioxide. Hydrocarbon emissions are formed in several areas within the vehicle: the fuel storage, delivery and the engine crankcase, called evaporative hydrocarbons. Tailpipe hydrocarbons are byproducts from combustion. Evaporative hydrocarbons are formed from the evaporation of gasoline petrol. They are formed wherever liquid fuel is stored or can gather. The fuel tank is the largest contributor to evaporative emissions, and as such has some fairly extensive controls to contain them. The fuel tank is designed with a vapour cell, used to separate and store hydrocarbon vapours for transport and storage within the carbon canister. Although the carbon canister is small, it is able to hold a very large quantity of vapour. The hydrocarbon vapours are absorbed by the activated carbon granules. When the emission control system determines that conditions are optimal, the evap purge solenoid is commanded open and the stored vapours are drawn into the intake manifold to be burned in the combustion chamber. During combustion, small amounts of unburnt fuel leak past the piston rings into the engine crankcase. These are known as blow-by gases. Blow-by must be removed from the crankcase before it condenses and reacts with the engine oil to form sludge. Not only will sludge block oil pressure galleries, but the unburnt fuel carried in the sludge acts to dilute the engine oil and cause premature wear of rotating components. Excessive blow-by gases will pressurise the crankcase and force engine oil past seals and gaskets, causing unwanted leaks. The positive crankcase ventilation valve is an emission control device used to remove excess blow-by gases from the engine's crankcase. The valve is mounted between the engine crankcase and the intake manifold. It may be formed as part of the cylinder head cover, the intake manifold, or be of a conventional separate external design. Regardless, they all function in the same manner. When the engine is not running, a spring holds a tapered valve or ball against the inlet port, effectively sealing the crankcase from the intake system and the ambient air. Any hydrocarbons are trapped, sealed inside the crankcase for later removal. Once the engine is started and it's idling, the tapered valve is drawn towards the vacuum source against the spring pressure. The spring is rated so it will compress under these vacuum conditions. The outlet port is minimised so only a small quantity of crankcase gases can exit to the intake manifold. These hydrocarbon emissions are drawn into the combustion chamber and are burned with the fresh air fuel charge. Under moderate to heavy engine loads, the vacuum applied to the PCV outlet is reduced. This allows the spring to push the tapered valve to a midway point within its housing. This is the widest part of the housing, so maximum crankcase gases are extracted at this load range. It's no coincidence that this is also when the maximum blow-by occurs. The PCV is designed to control and extract crankcase gases from a normally operating engine. Excessive blow-by gases resulting from piston ring or cylinder bore damage will not be effectively contained. Even in a normally operating engine, when the intake charge is compressed into the combustion chamber, portions of the mixture are forced into areas around the top ring land and cylinder wall, any crevices formed by the head gasket, spark plug threads and the valve seat. These areas are somewhat sheltered from the flame front and do not ignite during the combustion process. On the following exhaust stroke, the unburnt fuel mixture exits the combustion chamber via the exhaust valve as hydrocarbon emissions. All internal combustion engines produce some percentage of hydrocarbon emissions. Manufacturers try to limit this amount with efficient cylinder head, combustion chamber and piston designs. To control the escaping hydrocarbon emissions, manufacturers employ exhaust after-treatment devices and systems that further reduce or convert them. In most cases in a gasoline engine, tailpipe hydrocarbons are controlled by an exhaust catalyst. When the catalyst reaches its correct operating temperature, the precious metals adhered to the substrate core react or oxidise with the passing hydrocarbon molecules. Surplus oxygen from the combustion process, or released by the NOx reduction catalyst, combine with the hydrocarbon molecules, forming carbon dioxide and water vapour, or H2O. A downstream oxygen sensor is used to monitor the efficiency of the catalyst. If the substrate becomes contaminated or damaged, the oxidising process is inhibited, resulting in additional oxygen exiting the catalyst. The oxygen sensor reacts to this, and the resulting signal is interpreted by the ECM and an appropriate DTC is logged. Carbon monoxide, or CO, is a byproduct of combustion. It's a poisonous chemical compound of oxygen and carbon. CO is a colourless, odourless and highly poisonous gas that can cause dizziness, headaches and death by oxygen starvation. This is formed as a result of insufficient oxygen in the intake charge. In other words, by rich air-fuel mixtures. As the air-fuel mixture is leaned out, the CO levels reduce. Carbon monoxide will only be formed if ignition of the intake charge takes place. Nitrogen oxides, also known as oxides of nitrogen and NOx, are the various compounds of nitrogen and oxygen formed during the combustion process. The formation is a result when combustion temperatures exceed around 1200 degrees Celsius. NOx and hydrocarbon gases from vehicle exhausts combine in the Earth's atmosphere to form photochemical smog. Due to the way NOx is formed, the largest contributor to these gases is diesel fuel. Manufacturers have chosen several ways to control NOx emissions. Exhaust gas recirculation is the oldest and most common way to control this tailpipe emission. Unfortunately, it's also the most problematic. Very simply, a small portion of spent gas is taken from the exhaust manifold and channeled to the intake manifold, where it is drawn into the combustion chamber. This spent gas displaces some of the available oxygen which would otherwise be used in the combustion process. Lowering the oxygen content has the effect of lowering combustion temperatures. The EGR valve may work in response to ECM commands as to when and how much exhaust gas is recirculated. A reduction catalyst mounted in the exhaust may be employed to separate the nitrogen and oxygen molecules from each other. When the catalyst reaches operating temperature, the exhaust passes over the rhodium-coated substrate and a chemical reaction occurs to the NOx gases. The nitrogen is stripped from the NOx and passes uninterrupted out the tailpipe. The now abundant oxygen molecules are used by the oxidation catalyst if fitted, for hydrocarbon and carbon monoxide control. To control NOx emissions, many new vehicles use a selective catalyst reduction system. This is a chemical process where a reductant is injected into the exhaust stream and then absorbed by a catalyst. The most common reductant used by manufacturers is known as urea. This is an organic compound containing oxygen, nitrogen, hydrogen and carbon. The reductant removes the oxygen molecules from the NOx and combines it with the hydrogen to form a new compound, H2O. SCR works exceptionally well, reducing up to 90% of the produced NOx, although the catalyst temperature must stay within a specified range. The engine's control module is responsible for the quantity of urea injected into the exhaust. It must be proportional to the gas flow. SCR is much more common on heavy transport vehicles due to the amount of NOx they produce and the greater control over exhaust temperatures under long-distance highway driving. Limiting the amount of particulate matter or soot from a diesel engine's exhaust is the job of the diesel particulate filter or DPF. The DPF is generally located downstream of the NOx catalyst and is designed to collect and store soot particles in a substrate material. It's the sulphur within the diesel fuel that causes soot or ash to form when combustion occurs. The soot is burned off periodically during a process known as regeneration. The soot content is calculated by the ECM using data from the DPF pressure sensor. Carbon dioxide is not a pollutant, but has been proven in excess quantities to contribute to the greenhouse effect. Carbon dioxide is not monitored by the vehicle's emission system, but is a byproduct of combustion. In fact, high levels of CO2 equate to lower levels of hydrocarbon, carbon monoxide and NOx emissions. There's a very close relationship between the different exhaust emissions produced by a gasoline-fueled internal combustion engine. A lean mixture produces less hydrocarbon and carbon monoxide due to the higher air-fuel ratios, but lean mixtures create more heat within the combustion chamber, meaning NOx levels are increased. If we look at the CO2 levels for a lean engine, they will also be much lower than ideal. A rich mixture equates to higher hydrocarbon and carbon monoxide levels. In this instance, the extra fuel cools the combustion charge, lowering NOx levels. And again, the CO2 percentage will be low, indicating an inefficient burn. If the air-fuel ratio is perfect, hydrocarbon, carbon monoxide and NOx emissions will be low. The carbon dioxide levels will be high, around 14%. The vehicles we drive today have been built to adhere to strict emission rules and regulations. It's better to understand how these emissions are produced, so when a problem occurs, we can get to the bottom of it. Thanks for watching.